Continuing the story of the subtleties of limits and continuity in two variables, one of my favorite examples is just look at exponentials. Let's look at f of xy as x to the y. And to be simple, let's not let any of the variables be negative. But the subtlety here is going to be what about 0 to the 0, kind of a famous indeterminate form. So certainly if you look along the x-axis, positive x-axis, anything to the 0 power, if you set y equals 0, that's going to be 1. Okay, so that's illustrated by what's coming in along here. That's coming in along the x-axis. You just get this constant 1 value. And then if you set x to be 0 and y is bigger than 0, then that's going to be 0. Okay, now you might notice that that's not as obviously put into the picture here on the MATLAB plot. It kind of looks like it's starting out close to 0 but then ramping up, and we'll discover why MATLAB has a problem accurately representing this aspect of this function, and that's going to be an interesting illustration of what's going on here. So at 0, 0, traditionally 0 to 0 is undefined, but it actually, we're going to discover, makes a lot of sense in a lot of contexts to define it to be 1. And so let's just go ahead and put in a value to be 1. Okay, so at least it's going to be continuous now along the x-axis and not continuous along the y-axis because we didn't pick that limit value. The limit's going to be 0 because it's always 0 as you come in, and then suddenly we're defining it to be 1 right at the origin. Okay, so it's true that one of our standard procedures for detecting discontinuity and the non-existence of a limit in two variables is going to work here. If we've just picked the two simplest kinds of ways to approach that point, and we get different limits. Okay, so it's definitely not continuous. But it's interesting that if you just let's not allow ourselves to actually use the y-axis exactly. In the other example, like the train over the river example, we came in on all kinds of directions, and all these directions were giving us different answers. If I had excluded just one of those directions, I still could have detected that it's discontinuous. Okay, so, but here's what's interesting about this example. I claim that this guy is actually continuous along any diagonal axis, and you get the same limit every single time. You keep getting 1. Okay, so in fact, let's look at the colors here. The dark red is the 1 and the dark blue is the 0. What you notice is if you come in diagonally, like straight diagonally, you get through various colors, but I claim if you look at it, the red kind of dominates right here near the origin. And I claim, you can see that a little more clearly here, almost no matter how you come in, as you come into the origin, even if you're coming in really close to the y-axis, those blue, those kind of cool colors disappear, and eventually you get into the red zone. That's really why MATLAB is having such a trouble accurately representing the fact that it should be just flat 0 here. That edge that we're seeing is really where x is just a tiny bit bigger than 0 and not exactly 0. As long as x is just tiny bit bigger than 0, then it actually is going to give something that's close to 1. So here's the thing you just have to believe. Well, all you have to believe is the limit is basically ct to the t equals 1, as long as the c is not identically 0. So that's a straight line. That's parameterized, line parameterized by x equals ct, y equals t. In other words, it's the line where y equals x over c. It's going to be a nice straight line to the origin as long as c is not equal to 0. So that's not something I'm going to prove for you, but it's not super hard to prove when you actually use the technical things about limits. And you can verify this for yourself numerically if you want, or you can trust this picture that seems to be telling us, hey, it's really trying to get close to 1. Now, what's even more interesting is I told you that you can sometimes use curves to detect some subtle limits. This guy really wants to have this limit equal to 1. For example, what we could do, see this blue line on this other graph down here, what we're going to do is we're going to come in on this plot, so this is looking straight down on it again. Instead of coming in on a straight line like diagonal or really a sharp diagonal coming up close to the y-axis, we're going to try to be clever. We're going to try and come in along a line that starts out kind of, mildly diagonal, but then right at the end really hugs the axis. This would hopefully have a chance of seeing the fact that these values aren't really close to 1, even though they kind of seem to disappear. So we're going to try to sneak around the red zone and try to see if we can stay in the blue zone. Not with a square root, though. Okay, y equals square root x. What's a good way to parameterize that? If x is t squared, y equals t, then y is definitely the square root of x. So we're looking at the limit of t squared to the t. Well, that's t to the 2t, which is t to the t squared. But if you believe me that the limit of the t to the t is equal to 1, then that squared is also equal to 1. Same deal with cube root of x, fourth root of x, fifth root of x. All those guys hug the y-axis tighter and tighter and tighter, and yet we could never get 1, or we never get 0. Okay, we always get 1. So we seem to always get 1 unless we're on this extremely special case of coming in perfectly along the y-axis. Well, that's almost true. It's true as long as this is anything just built out of pure algebra. Okay, just like roots and powers. It's really trying to be 1. That's why, as I said, it actually makes a lot of sense to define 0 to the 0 to be equal to 1, because it makes this thing almost continuous, except if you really try hard to hug that y-axis. Now, but I haven't shown you that there's no way to hug the y-axis besides the y-axis itself. We know that if you come in straight along the y-axis with x set equal to 0, the limit's going to be 0. And that's certainly an issue. And in fact, you can, if you're clever enough and sort of extreme enough, you can get a curve that hugs the y-axis tight enough. So here's the red curve. This red curve is the graph of, let's see, I forgot to put it in. It's x equals e to the minus 1 over y. This is a famous kind of function that hugs this y-axis tighter than any possible root function, even though those guys can hug pretty tightly. Another thing that I don't want to spend time talking about, but it's a function that's very cool to investigate. It has a lot of cool properties. Now, if you put that in, we get to use rules of exponents again. E to the minus 1 over t to the t, these things multiply and cancel. I just get e to the minus 1 or 1 over e, and that's definitely not equal to 1. And it's interesting that it's an intermediate value. So you can kind of sneak in here in a way so that you're never along the y-axis, so you never actually get 0. But you're staying away from the red zone, and you can kind of pick these guys. So what we're really doing is we're discovering, you might notice that this red thing kind of looks like one of these curves. We're really, it's almost the yellow curve, in fact. We're really just picking a contour line and staying along the contour line. Oh, that should have been, maybe that should have been obvious. Maybe you could have seen that already. If I just figure out, oh, I know what these contour lines are from the plot, just stick along a contour line. Whatever that funky curve is, it should allow me to have that limit. Let's say the yellow is 1 over e, maybe, and as the height, then I'm just going to stick along that contour line, and that's going to give me that limit. If I want something smaller, I use the blue, or I use the light red instead of the dark red. But then the question was, what is this contour? What is this graph? Well, it's this kind of function. Now, could I actually get 0? Okay, these guys are all going to give me a bunch of non-zero, non-1 numbers. Well, a good way to do 0 is get it even more extreme. Something that hugs the y-axis even tighter than these funky contours, even tighter than this red curve, is e to the minus 1 over t squared. Well, take that to the t power. It kills one of these in the denominator, but not both. You get e to the minus 1 over t. And my claim is that the limit's equal to 0. That's not too hard to verify in itself. T goes to 0, 1 over t goes to infinity, minus 1 over t goes to minus infinity, and an exponential of a big negative number is very close to 0. Okay, so in fact, there's various ways you can kind of sneak around this graph to get all kinds of different limits, which is illustrating that, yes, it is discontinuous at the origin, but it's interesting how much work you have to go to actually get any limit other than 1. So, another illustration of the possible subtleties.